So we have introduced the concept of sequential compactness. A subset A in Rn is sequential compact if any sequence in this set capital A there has a subsequence xki, xki converges to some point in capital A. Okay, this is the concept of sequential compactness. I will remind you that this is limit small a is not fixed. For different convergent subsequence xki, you might have a different limit small a. Okay, so this a is not fixed, not the same one for every sequence. This is not true. The a depend on the sequence xk, even depend on the convergent subsequence you choose. Okay, I will remind you this. Now, sequential compactness is very important. Therefore, we need to be able to verify whether a given sequence is a sequential. Whether a given subset is a sequential compacted. Okay, but we have a very simple theorem which describes the sequential compacted set completely and very easy. Okay, the result is that A is sequential compact if and only if A is bounded and closed. Okay. So this uses our familiar concept boundedness and closedness to describe the sequential compactness. Okay. So the proof of this theorem is also easy. We prove the only if part first. So we know that A is a sequential compact. We want to prove that A is bounded and closed. Okay. So first we prove that A is bounded. We argue by contradiction. If A is not bounded, bounded means that there is some number R such that every x in A, the norm of x will not greater than R. Okay, this is the boundedness mean. So if A is not bounded, then for any number R, there is x in A whose norm is greater than R. We take R to be 1, 2, 3, 4, be the positive integer. So if A is not bounded, for every positive integer k, there will exist a point denoted by xk in A such that the norm of xk is greater than capital K. Okay. So xk is a sequence converging to infinity. We know that any sequence of xk for any subsequence xki, of course, the subsequence also, the norm of a subsequence also converge to infinity, also approach infinity. Okay. Okay, so this sequence could not be bounded. This subsequent could not be bounded. Okay, but a very easy result tells us that convergent sequence is bounded. An important fact. Convergent sequence must be bounded. Okay, this means that this subsequence could not be convergent. So from the assumption that A is not bounded, we can construct a sequence xk in A. Every subsequence of this sequence is unbounded, therefore could not be convergent. So this is a contradiction to the sequential compactness of A, right? So this proves the only if part of this theorem. Okay. Now we will prove the if part. If part. So we know that A is closed and bounded. We want to prove that any sequence in A has a convergent subsequence. Okay. No. Sorry. The only if part had not completed yet. We only prove that A is bounded. We also need to prove that A is closed. So for the only if part, we have proved A is bounded, right? Because A is not, if A is not bounded, we can get a contradiction. So A is bounded, but we also need to prove that A is closed. Now we prove that A is closed. So if A is not closed, if A is not closed, then by definition, there exists a sequence in A which is converged, but the limit is not in A. Okay, closeness means that any convergent sequence has limit in A. So therefore, to declare that a set is not closed is equivalent to say that there is some sequence in A, although it converges, but the limit is not in A. Okay. So this sequence, for this sequence xk, this sequence in A, any subsequence converge to the same limit A, but A is not in A. This contradicts the sequential compactness of A. Okay, because A is sequentially compactness, means that any sequence in A has a subsequence converge to a limit in A. But here, for our this sequence, it is not possible to have a subsequent converge to a point in A, because any convergent subsequence of our xk must converge to a point not in A. Okay, so this is a contradiction to sequential compactness of A. Okay, so this completed the only if part of the theorem. Okay, now we need to prove the if part. If part. So we know that A is bounded and closed. We want to prove that A is a sequential compacted. Okay, so to see that A is a sequential compact, we take a sequence in A. So by definition, we need to find the convergent subsequence of this sequence xk, whose limit is still in A. Okay, so this is what we want to do. We need to find a subsequence xki such that this subsequence converges to some point in the set A. This is what we need to do. So our A is bounded and closed. So since A is bounded. The sequence as a subset of A is a bounded sequence. Okay. Previously we have a result saying that any bounded sequence in Rn has a convergent subsequence. So xk has a convergent subsequence denoted by xki. So xki converges to some point A. But we don't know whether this limit A is contained in the capital A. We don't know this. But because A is closed, and our subsequence xki as a subsequence of xk, because xk is in A, right? Xk is a sequence in A. So we also have xki is a sequence in A. Now xki is a convergent sequence in the closed set A. Closedness means that the limit belongs to A. So by the closedness of the capital A, our limit of this subsequence belongs to A. So this altogether means that for any sequence in A, we can find a convergent subsequence xki whose limit small a belongs to our set capital A. So this means that the set A is sequential compact. Okay, so this proves this theorem. So to verify whether a set is sequentially compacted, we only need to prove that the set is bounded and closed. Okay, according to this theorem. Now we will investigate some example. B is this set X in Rn. The norm of X is not greater than some positive number R. We declare that this B is a sequential compact. B is sequentially compact. Okay. This is easy because this B is bounded and closed. Okay. B is bounded and closed. Why it is bounded? Boundedness means that there is some number rho positive such that the set contained in the ball with radius rho. Okay, this is the definition of boundedness of a subset. If the subset contained in some ball which is sufficiently large radius, then this set is bounded. But our B is a ball. Our B is a ball which the boundary sphere, the sphere is the norm equal to R. Okay, so our B is a subset of we take rho equal to R plus 1. Okay, so this proves that B is bounded, and B is also closed. This is also easy. We prove that so we already don't know that B is bounded. Now we prove that B is closed. So to prove B is closed, we take a sequence xk in B, and the xk converges to some point A. To know whether B is closed, we only need to know whether the limit belongs to B. If the limit always belongs to B, then this implies that B is closed. Okay, but this is also very simple. Xk belongs to B means that xk, the norm of xk, is not greater than R. But xk converge to A, xk converge to A means implies the norm of xk converge to the norm of A. Okay, we have many methods to prove this fact. We can use the triangle inequality. The norm of xk minus the norm of A. So this is the difference of two positive or negative number. Then we take the absolute value of their difference by easy corollary of the triangle inequality of norms. We know that this will not greater than the norm of xk minus A. But the xk converge to A, so this norm goes to 0. So this implies that the norm of xk goes to converge to the norm of A. So combine these two together, the norm of xk is not greater than R, and the norm of xk converge to the norm of A. These two together will lead to the norm of A is not greater than R. Therefore, A is a point in B. So this proves that B is closed. Okay. So so this B is closed and bounded. Therefore, it is sequentially compact. Okay.